Hello, Mike.
Hello.
Hello, Bjorn.
Hello.
System working?
System working? Seems to be. Shall we get rolling?
Let's start. Hello, everybody. Welcome to Beam There, Done That podcast. I'm one of the co-hosts, Alan Wyma, and today we have two very special guests, but of course, starting with our very own special guest, Francesco Cesarini.
Hi, I'm Francesco. I'm also co-host. So, how do we introduce our special guests? Well, we spent the series tracing where Erlang code runs, and we've had Björn talk about the Beam, we've had Lucas talk about the JIT, we've had Maxime, talk about Ling running under bare metal. Today, what we're going to do is we're going to go back to the very, very beginning. Before any of these VMs, we had the Jam, Joe's abstract machine. It was the first virtual machine that made Erlang fast and allowed it to be used in production. I personally came across the Jam for the first time in 1994. So this was 5 years before it was released as open source. And I went on to use it in production on multiple projects before we all started migrating over to the Beam. So this is a very, very personal episode for me. And we've got two of the best people placed in the world to tell us the story. So we've got Mike Williams, one of the creators of Erlang, who actually, despite the Jam standing for Joe's abstract machine, he wrote large parts of the emulator himself. And we've got Björn Gustavsson, the Beam, who joined the team in 1996 and built what came after. So, Mike, you were there first. Let's start with you. Before we get into the machine itself, to the virtual machine itself, why don't you introduce yourself to the listeners?
Well, I'm Mike Williams. I worked at the time, as everybody else did, in the computer science lab at Ericsson. Our objective was to try and do something about the state of real-time software for telecommunication systems at Ericsson. And we had a mandate to sort of basically do whatever we wanted, which is rather surprising because Ericsson doesn't normally work that way. I previously to joining the computer science lab have been working with several other real-time systems, mainly in structured assembly languages for the Motorola 68000, and prior to that to some of Ericsson's home-built computers. So I'm really not really a educated programmer at all. I actually learned C at the same time as I was working with the Jam. I'd not actually worked with C before that. Nothing much more to say about me, but go on with the rest, yeah?
Björn, what about you?
I worked at Ericsson in 1996 with something completely different. And then I happened to meet Tony Rågvall that worked with Erlang in the CS lab at the time. We happened to work next door in the same building in Älvsjö. So I just happened to meet him on the bus home. And he said, I should come and work with Erlang. And so I did. So I went there and I was expected to do an interview to start working with the P team. But Mike was there. I met Mike and he asked me to come and join a project in Kungens Kurva called ANX. And he said I could quit at any time I wanted and start at the UTP team. But so I worked 6 months with that project, and then I went to UTP team at the end of 96.
And it was the ANX project where we worked together and first met. So what it did was, it was Ericsson's broadband solutions, looking at a variety of protocols. So, Mike, before we get into the Jam itself, you wrote the emulator, the C code that everything ran on. In his, History of Programming Languages paper, Joe Armstrong describes you as taking over the inner loop, throwing away his code, and then working for days to get the message sent just right. Stopping only when it was down to 6 instructions. That's a very, very specific kind of obsession. Can you take us back to that? What were you
I
actually
think
fighting with?
I think we have to go down before that. The original thing was the emulator in Prolog, which was used. It was actually never intended to become a system in operation. It was always intended to be a system for what was then in fashion, which was rapid prototyping. But when we got it working and people were using it for rapid prototyping in another subsidiary of Ericsson in a place called Balmora, that we realized that maybe we could get this working. So Joe had looked at the Warren abstract machine and had vaguely got some inspiration from that about what to do. He then started doing a little bit well, and I think he wrote about sort of 20, 30 lines of C, and then he can with home compiled instructions. And I looked at it and said, Joe, it can't really be like this. I mean, I'm not a C programmer, but this is awful. I'll do something about it. So it wasn't really as much actually getting the message passing to working. It was actually getting the loop itself to working. I mean, there were weird things at the time. At that time, we were running on VAX VMS systems, and the C compiler wasn't the world's best. For example, that the JAM is a bytecode interpreter. And so what that basically means is you have a big switch statement for the possible 256 instructions. One thing I discovered fairly early was that the compiler did a bounds check on a byte to check that it was under 256. Which obviously, since you go around that loop very frequently, slowed down the machine incredibly. Then a bit later, we said if this is going to work, we have to sort of look that in the sort of real-time systems we were looking about, concurrency and getting concurrency working faster meant that the scheduler and the message passing were absolutely critical, because those actually sort of used much more code than anything else. So I hacked away at it, and I had at one stage an awk routine which massaged the code to get rid of bounds checks and that sort of thing, which got it going a bit faster. Then, of course, it sort of the people in Balmora said, "Hey, wait a minute, we use this for prototyping. Maybe we can actually use this for a real system. I mean, have a look at it." So the goal was to get it fast enough for the system that they wanted to produce at the time, which is called the mobility server.
I think we'll be covering a lot of these, Alan cut this, covering a lot of these questions moving forward. We've also, covered the mobility server at length as well. So try to condense them a little bit, because you'll notice, I think all of these things, we'll come back to them now. So great introduction, yeah.
Bjorn, you basically inherited what Mike's built when you joined in '96. The JAM was already the production VM for Erlang, and you go on to actually replace it. Was there a moment looking at the JAM where you thought, okay, this part was very brilliant, was very amazing, was very great, and a moment that you thought that this piece it's really not up to standard. We could do it much better. And what did you know immediately that had to change when looking at the JAM?
I didn't really see anything directly need to change. I knew that the Beam was much faster, but Beam was also much more complicated and messy and used a lot more memory. So I actually liked JAM when I started working with it. It was clean and used little memory for the code. And the JAM files were also smaller. So it was only when we had a better version of Beam, more stable of several years of work, that it was becoming cumbersome to implement features for both JAM and Beam and make sure they worked on both.
I'd like to go back one step further and talk about what actually became before the JAM itself, right? It wasn't even on any kind of virtual machine. It was on something totally different. Maybe this is a question more for Mike. Can you talk more about the step before the JAM?
Well, basically, it was a Prolog interpreter of the instructions. It didn't really have much concurrency or anything like that. That it just instructed that it was painfully slow, but it was perfectly all right for what people wanted it for at the time, which was prototyping.
I think Joe, in his Hopple paper, the History of Programming Languages paper, said that it runs at around 4 reductions per second, so basically 4 calls per second. Why wasn't that good enough? What forced the move to a real virtual machine?
If you want to run it on a machine, it obviously has to be much, much faster. And for a real system, the Prolog system was just not good enough. That the Prolog was preceded by a lot of other attempts to try and get it faster we didn't actually have to build our own machine. We experimented with a language called Parlog, which was made by a company in Britain. And we also experimented with Occam, which was also made by a company in Britain. It was obvious that we had to do something which would run on a sort of fairly normal commercial machine. It was just simply speed was needed, and also memory space was needed. You remember in these days we were talking about computers with a minimal amount of memory and laughably slow.
We had 3K on my Commodore VIC-20, so yes, I remember that. But so running on Prolog, did that affect the syntax in a way, or are the two unrelated?
The syntax comes from Prolog, that statements that ended with a full stop. The funny arrow that you have in for function calls comes from something which you could run on top of Prolog called a DCG, a direct call clause grammar. And it was that was being used to some extent for prototype. I at the time said that to Robert that I think that we're going to get rid of this syntax and put something a bit like C or Pascal, so people feel a bit more comfortable. But Robert disagreed with me and thought it was essential to have a different syntax, and he liked the Prolog syntax. Mind you, if we'd let Robert free, I bet we'd landed out.
He still does today. He still loves the Prolog syntax today. We had him on the show. He was very, very vocal about it.
Yeah. I think if we'd given him a free rein, I think he'd probably had the language with lots of brackets right and left instead.
And some of the choices you made in the jam are still in the Beam today. The per process heap, the copying messages between processes rather than sharing memory. Mike, those were in the jam from the start, or this is something that you came up with yourself, or because there was a lot of discussions, I believe, happening all the time within the laboratory. So I'm kind of curious about those ideas, about when they were put into the jam and who's kind of pushing those ideas and whose ideas those were, if you can give some more context.
Well, it wasn't really that we had those ideas. It was just that those ideas were necessary. For example, that although the first systems weren't distributed, if you have a distributed system, you have to have copying messages because you can't copy over a processor boundary. Well as that any idea of using the native concurrency in the machine itself was completely impossible, because the processes at that time on Unix that we were running were just far too heavyweight for the sort of concurrency we needed. So these weren't really decisions which were made. They were they were just things which became absolutely necessary.
Now, Bjorn, those choices that Mike just described, and how many of them did you keep when you actually built the Beam? And also all the other choices you've seen with inside the jam and so forth?
Yeah, we kept all of those message passing, copying, and so on. No change there. We only changed some minor implementation details. Beam and Gem shared the runtime system, and we have some conditional compilation to do there was some difference. Beam did garbage collection inside BIFs, and Gem didn't. But we changed that later to let the Beam do as Gem did, which was to allocate a new memory, what we now call heap fragments. When we need to allocate memory in a BIF, we allocate the different memory. We don't do garbage collection as Beam used to do. And that was, Gem did that from the beginning. It's much simpler.
So, Mike, one property that was there from the start, and one for which Erlang is famous for, I think it was first documented and referenced in 1992 in a paper you and the lab presented at the Software Engineering for Telecommunication Switching Systems. It's basically changing code in a running system without stopping it, software upgrade during runtime. And in this paper, you described how this worked, through an export table. You load a new module, you swap, the reference from the old version of the code to the new version of the code, and any new code which gets executed, any new calls will hit the new code. Can you walk us through that? Why was the ability to do software upgrade during runtime non-negotiable?
The reason was that the whole of the Erlang project, if we like to call it that, was to be able to replace a previous system of Ericsson, which is called AXE Plex. And one of the things that you could do in that system was replace code on the fly, which was absolutely necessary to be able to do be able to keep systems running continuously, which are, in fact, there are legal requirements at those stage about how often your telecommunication system as a telephone switch can go down. So it was absolutely necessary to be able to do that. And an anecdote there is we demonstrated the Prolog interpreter for our then manager's manager, Tubin Johansson. And during that, we changed code in the Prolog system, which of course is very simple. You just simply consult a new file. So we could do that, and we didn't actually think about it very much. And Tubin was very impressed. He said, "Gosh, can you do that?" And I said, and Joe said, "Yeah, of course we can do that." The only problem was in the jam, you couldn't do that. So I had to spend the next fortnight thinking about ways to do it. And this is why the rather arcane way of changing code actually came about. And I managed to get it working. There is only one. It really replaces what you might think was the patch system, to be able to change the assembly language in the AXE systems, and that of course is it's an emulator of the same thing. Although it came to be used a bit later to replace whole modules.
Now, Mike, speaking about modules, right? The part that kind of surprises some people is that Erlang lets you have two versions of a module loaded in at once, the old and the new, but only two versions, not three, not 50, not 100. I mean, we're performing probably lots of hot code upgrades with what the original intent of the system is. Now, what was the driving for that? Why even put a limit on it at all?
It got far too complicated to do anything else. I mean, if you're going to have a version 3 of one module, does that run with version 7, 8, or 9 of the other modules all the way it works? It would just be impossibly complex to design a system which actually could be guaranteed to work with multiple versions of different modules.
Were there any, so simplicity was key. Were there any memory constraints?
Yes, of course. So then at that time, we were running on small amounts of memory, and every new module required more memory. You would have required, it would have been very difficult. You'd have had to have many of the keys, so the tables inside the jam would have had to be duplicated. And it was memory, and it would just simply, it's mind-bogglingly impossible to work out how you'd actually get that to work.
Björn, so this two-version rule Mike just described is still exactly how the Beam works today, 30 years on. Did you ever reconsider it? Or, was it right for the time? Is it right for today?
It has been suggested a few times that we should actually remove that limit and have unlimited number of modules, but we never wanted to do that. Basically, for the same reason that Mike talked about, it would be a trap for anyone designing a system. They could have old code running or that were not expected, waste memory and running very old code leading to surprises. So we didn't think that was a good idea for application programs. So it would be a trap for them.
Mike, in the History of Programming Languages paper Joe Armstrong wrote about Erlang, he credits you with hammering into his brain the three things that decide whether a concurrent language lives or dies. I don't know if you remember that. And the three things are, the time to create a process, the time to context switch between processes, and the time to copy a message between them. And he says that the performance of any highly concurrent system is dominated by those three. Where did that convention come from? You and Bjarne, and Bjarne, for those who don't know him, he was, the head of the computer science laboratory and the co-founder. He had been, you and Bjarne had been doing concurrency for quite a while, long before Erlang.
If you actually go back in history to a paper that I wrote and presented at a conference in Eindhoven much earlier, I looked at the amount of time required by a system, how much time you're actually running, what percentage of the time you're running application code, and what percentage of the time you're actually running doing the virtual machine, doing context switching, passing messages, and everything else it does. And you could see that about 70% of the time is actually the virtual machine doing its internal stuff, and about 30% of the time is actually running application code. I don't know what it is today, but I suspect it's something very similar. Of course, depending on what the machine is actually doing, or what your application is. But the applications we had, that was definitely measurable.
Yeah, I just researched the paper, and you're referencing Mike. I think it's the development of Erlang from.
No, no, it's no, it's not that. Not
Okay,
that.
it's
It
not.
is
That's
efficiency of executive systems in telecommunication systems in
oh,
Eindhoven, and I guess in Eindhoven in about 1983, 84, maybe something like that.
I'm going to look
It'll
it
be
up
in
now. I'm
beyond.
really curious.
It'll be in Björn's thesis if you look for it.
Yes. Okay. Yeah. Yeah. Okay.
So if those three numbers, right, those three things that you really wanted to get down pretty quickly are what matter, how did that shape what the jam had to be? And what did optimizing those for those three different numbers actually force you into when you actually started to work on those, optimizing those?
That it forced one into sort of doing very little internal checking, and that's making sure that bounds checking I mentioned earlier, and that sort of thing. It felt you're just streamlining the code as much as you possibly could. And when I stopped working with the jam and Tony Rogvald took over, he optimized it even further. I never got to the jam working as far as distribution is concerned. I had a sort of distribution working, but later on other people took over and I moved on to different things.
I mean, in a way, this is the heart of it, and it's one of the things when I first started using the jam, which took me a few days to realize. And in Erlang, you've got processes which are, part of the language and not the operating system. And this goes back, to these, pre-optimizations you've just described. And the history of programming languages paper is very, very blunt about it. Joe writes that when Erlang was first implemented, the view that processes belong to the language rather than the operating system was not widely held. And even today, I'd almost go in and argue that it's a minority view. It's changing, but it's still a minority view. Go back to the early days of Java. It had green threads when it first came out. They were removed. Rust was just the same. It had lightweight processes. For some reason, in the very early versions of it, they got removed. Mike, so when did you decide to separate the concurrency model away from the underlying operating system? Was that a decision, or was it never the operating system's job in the first place?
It was never the operating system in the job in the first place. It was perfectly obvious that we could not use operating system processes for what we needed. That prior to that, I'd been working with languages called Eric Pascal, and prior to that, a language called PL163, both of which had their own operating system, executive systems. It would certainly been possible to make Erlang use native operating system processes, but you'd have had to rewrite and make your own operating system, and that really was something we just didn't want to do. That was just it would have caused far too many problems.
Not using the operating system's threading model, right? Why is this a language level process? Why is language level processes better than OS processes for this? I mean, if you think about it, letting the OS handle more things for you lets you focus on other pieces of the aspect of the language. But at the same time, that actually has brought a lot of flexibility and things are easier with it nowadays, right? So, what was the thought at the beginning of this that made you really think about this was a good idea?
Well, it was simply that if you looked at context switching in Unix or Solaris at the time, we were using at the time, and you looked at the amount of memory required by each process, that we were talking about systems already then, which were going to have thousands or hundreds of thousands of processes running at the same time. So it just sort of, you just have to do the maths. It's just impossible to work.
Going back, and when I was researching this episode, I think the languages which I think shared the view of separating the concurrency model from the underlying operating system at the time, I think included Ada, Eric Pascal, Chill, Plex, I think Euclid as well. It's a language I haven't researched that much. And actually, even Smalltalk, even though we didn't call processes, they were actually called objects, but the principle was still the same. And I recall, I think, there were hard limits when on the hardware I was using when I first used the Jam. I think we could have a limit of 32 threads, but I
No, no,
clearly
no.
recall that during
It was much more than that.
much more than that. Okay, I think this was 90s, early 90s.
No, I can't remember what it was, but we were still talking about hundreds or if not thousands of processes then.
Yeah, but it was clear, everyone else, thought processes were the kernel's business. Björn, let's fast forward a little bit. In August 2006, the OTP team shipped Erlang on SMP, on multicore. The share nothing, pure message passing decisions taken in the late 80s and early 90s produce code which runs beautifully on multicore. Most programs just go faster, and they go faster without having to rewrite them or do anything about them. I think I remember the XD301 had a almost 100% increase when it went from single core to a multi-core architecture. And this is a payoff which came 20 years after Mike and his colleagues at the Computer Science Lab made the call. Did it feel like collecting a bet someone else had placed?
Yes, in a way, yes. So that architecture saved us a lot of work when we implemented the multi-core. It still took us about a year to get the first version working. It was mostly Richard Green did it, but it would have been much harder if there had been a global heap shared. It's much harder to get that with good performance.
We usually joke, Erlang was built from the web, even though it predates it, and it was also built for multicore, even though it predates it too. So yeah, it's. So the Jam made Erlang fast enough and got the concurrency model right, and then it was replaced. And the thing which replaced it was with the Beam. For the listener, what was the Beam at the time, and why did it win? Why did it go in and actually replace the Jam?
Beam was a faster machine for running Erlang. It was not a stack machine, it was a register machine and had many optimizations. But you shared the source of a runtime system with Jam, so it would be compatible. And because it was faster, people wanted something faster. So when Beam was stable enough, we could drop Jam. But we had to work several years to achieve that, fixing thing, making Beam as stable as Jam was. Jam was rock stable. I don't think I ever fixed any bug in the Jam part of the runtime system. Bugs were in the beefs, for example, and in the Beam part, but almost never in the Jam part, as far as I remember.
Yeah, I do recall. Yeah, I think I got one crash of the Jam, and that was back in 1994 when I was in university. And since I never have seen it crash, even though the crashes with the Beam in the early days and the XA301 were rare, but they were much more frequent. And just for the record, a Beam stands for Bogdan's Erlang abstract machine. Many says, Björn is the B in Beam, but you actually went in and took over what was originally called Turbo Erlang, and then went in and redid it. And when you were doing that, what is it when you started working on the Beam? So you took the Beam, which was an existing implementation, instead of starting something from scratch. What did you actually port over from the Jam, and what did you throw away?
They share the same runtime system, so we kept the runtime system. And then in Jam, in beefs, when a beef need to allocate more heap memory, it would allocate a new memory block, something that we call heap fragments nowadays. But Beam would do a garbage collection, and that was very complicated to make sure that it got right, so it didn't crash when doing garbage collection. You have to make sure that you have access to all roots of terms, so you didn't lose any term in a garbage collection. So we decided to do garbage collect, do it the same way as Jam for that, to just allocate more memory. And then we will do a garbage collect a little bit later when we're out of the BIF. So that we inherit from Jam.
It almost sounds like a lot of that was about memory. And, in the mid 90s, on board memory was around, 256 megs. In the early 90s, I mean, we were actually shipping systems on 16, 32, and even 64 megs. And these were systems which, were handling phone switches for whole cities. So Joe says, concerns about object code size, lay behind many of the decisions in both the Jam and the Beam instruction sets, and that the binding constraint was memory and not speed. And again, this comes from the History of Programming Languages paper Joe wrote and presented.
Yes, I spent a lot of time optimizing the amount of memory the Beam used. Beam instructions were much larger before, and then I found ways to make them smaller. For instance, for instructions that have multiple operands, in some cases, operand can be packed, 2 operands into one 32-bit word. So saving one word, for example, and I've found other ways to reduce the size of Beam instructions. Also, the Beam files were much larger before, so that was also a concern from customers. Disk space was also had limits, so I also reduced the size of Beam instructions in the Beam files.
I want to start to kind of bring this all in and talk a little bit more about, at the computer science lab. From my understanding, the way things usually work is that there's a lot of conversations happening, right? People discussing things, sometimes a little bit more heated. I know I had an interview with a guy who used to do a lot of academic work, and our discussions weren't really discussions. They were more like arguments. I'm guessing that maybe it was similar at the laboratory for you guys. So, a lot of these discussions are happening. You have this brilliant idea, you bring it in, maybe it gets torn down in not the nicest way, but in terms of, trying to make progress, there's a lot of these discussions happening and not many people actually at the keyboard pounding out code until that's the very last step. So when you're having all these discussions, you're bouncing back and forth. Person A says, A, the next person says A1, A2, I think like ideas start getting better and better after discussions. But over time, people say, well, I remember that this was my idea and I remember that this is my idea. Is that kind of, basically what happened with Erlang is that everybody remembers that some of these features are, their ideas and not others. Mike, can you discuss more about your time over there and discussing ideas?
I don't think it happened like that at all. If you look at an academic perspective, one thing that people do there is publish papers. I mean, that basically is what academia is about. We didn't publish papers. We had a paper or two now and again, but our object was not to sort of increase the number of papers published per person. And therefore, sort of who owned what and why things were done was more interested in getting it done, not how many papers could we publish. So I think that's one thing which goes wrong in a lot of academic backgrounds, that they're more interested in getting research grants and publishing papers than actually doing the job. But the example is that we tried to get academia to be interested in Erlang. And it was only when it began to become a success that we got Uppsala interested, the university there. But prior to that, we tried to get people from SIX, the Swedish Institute of Computer Science, and the Swedish University in Stockholm interested. And they just weren't interested because they couldn't publish papers and they didn't get grants based on that.
One idea that I heard was yours was all about the idea of process linking. And you also took it from the telecom industry. Can you talk more about where that came from and how that came into the language itself?
There were two things that, if you looked at old-fashioned mechanical exchanges, they had something called the C-wire, and that held all complete. It was kept at minus 48 volts. And if you earthed that, and the whole of that call all the way through the system collapsed, which was a sort of transaction handling in mechanics. That came again into the AXE system. The large bit was the AXE system, which gave us the requirements needed for Erlang, which produced a system which he came over the Swedish name for LOP, badly spelt. But getting a transaction system was necessary. And the obvious thing, if you have a number of processes which are working together, if you collapse all of them, you get rid of that transaction. The nice thing about telecom systems, compared to a lot of other systems, is that you don't have to do much recovery of each transaction. Because if you collapse a telephone call, whether it be a mobile call or another one, someone else just makes the call again. So the recovery is done for you by the user without the user really thinking about it. It's even better in mobile systems because people expect calls to fail because you go through a tunnel or you lose coverage on your phone, and therefore losing a mobile connection is actually sort of just what happens. So the whole idea was to sort of to create a system where you can make transactions. So linking processes, one thing I got wrong there is I made processes double linked instead of single linked, which was corrected later. And but the whole framework there was something I sort of dreamt up because it had to emulate something that had been done previously.
Bjorn, you joined in '96 after a lot of this stuff was settled. These crazy, very interesting ideas that turned out to be very great for building very resilient systems. I mean, what was it like walking into that? Did you hear about some of these ideas before? Have you seen them in other languages, other places?
No, I think it was pretty new to me, concurrency and so on. So I had to learn all that when I started.
Now, what about the culture that Mike described at the laboratory? Did you feel it was the same?
Yeah, I think it's similar now that we do things more informal. We don't write a lot of specifications. We maybe become a little bit more formal. We have EEPs, Erlang enhancement proposals, that for at least for bigger stuff, we write that down and we discuss it with the community beforehand. But we do a lot of things just sitting down and drinking coffee and discussing, coming up with ideas.
I mean, there's a lot of history involved with creating the beam and of course the jam and everything else. There's so much history in there. I mean, there's like decades of history. Where can we actually go to hear more about some of the history of what's happened? I mean, maybe Mike, you have some speeches that you gave or some talks that you're aware of that talks more about this.
I don't really think so. I think Joe's history paper and the papers which done at SET's conferences were sort of to describe the era with which I worked. Then, of course, I think that one has to sort of give a lot of credit to Uppsala for the work that was done there in getting native Erlang working. That I don't think there's much actually documented in this at all. Bogdan, of course, documented his operation of Erlang. That I remember that he was trying to tell me that he wanted to call his paper Carpe Diem. And he said, "What's that in English?" And I said, "I don't know, it's Latin."
We're showing on the screen right now Joe's paper, which he wrote for the history of programming languages. You can just Google History of Erlang, Joe Armstrong, Ericsson, AB. And at the bottom of it, it's got a long list of references which I think contain a lot of the very early papers. Telephony programming in Prolog from 1986, using Prolog for rapid prototyping 1989, and many, many others. And I'm sure they can still be found in digital format in some shape or others. And the second I also want to recommend is Bjarne Dekker's Licensate thesis, where he basically describes what the computer science lab was all about, how to solve a problem and, figure out how to program telephony switches. But the fact that the properties displayed by telephony switches when the internet came about became much, much broader and applicable to a large set of other verticals. In conclusion, when I first started using the jam in 1994, I was a student at Uppsala University, and I really recall my surprise when I went in and typed PS minus CF and realized that there was not a one-to-one match, between threads and processes. And at the time, I think I realized early on, even though I was still learning, that I was looking at a very, very clever piece of software. And I came to the realization, when I then, the year later, joined the computer science lab to work on my thesis project, that I was looking at the decisions of about half a dozen people, so with Joe, Robert, Bjarne, Mike, and many others around them. And many of those decisions are still running, systems worldwide today. And they're also the decisions which have allowed Erlang, to become not a programming language, but an ecosystem of languages. Mike took concurrency out of the operating system because he knew, which big free numbers mattered. Joe, built a language. Robert rewrote it, and he kept on rewriting it. And he probably would still be rewriting it today, knowing Robert, had there not been a deadline. But he keeps on rewriting it, and he rewrote it until it was right. And Bjarne stepped in and gave everyone the space they needed to be innovative and creative. And I keep on repeating, none of them would have been able to do it alone. But put the dream team together in the same room, having breaks around the same coffee table, give them the space they need, and that is where things start happening. So, and very, very glad to be able to actually go in and record this and get the world to know about it. So this is what the Beam They're Done That a podcast is all about. It's the people behind the design choices the rest of us are still using today. So if you're new to the show, don't forget to press subscribe. And from here, we'll now be working forward. Mike, Björn, thank you so much.
Can I make one last comment?
Absolutely.
There are one person whose name is never mentioned in this context when he was very important in this is Claes Wikström, who actually invented ETS tables, was the person originally behind the database Mnesia, and took my code and introduced it and put in distribution. Without Claes, we wouldn't have had Erlang as it is today. So that for some reason he tends to get forgotten in this discussion.
So true. Yeah, so true. So shout out to Klacke as well. Hopefully, we should get,
Can I also mention about Klacke? He made a prototype of the bit-synced or binary syntax together with Tony Rågvall. So that prototype inspired us. We implemented in R7B in Beam.
That is correct. And it was a great prototype, I think, which was presented at the Erlang user conference. So it's in the proceedings there. So, absolutely. And I think this is all of the history which, needs documenting. So, and I think, this is an episode which we recorded today, which we'll be sending a lot of listeners back to, So thank you for joining. And just for the record, this episode was recorded on the 4th of June, 2026.